waiting for must be really important.
Oh, usually we're waiting for you, not today. I'm just waiting. I mean, I can't imagine we can start on time. So I'm just waiting for not to start on time. Okay, now it's 4:16. So are there people on Zoom? It's hard to say. Okay. Anyway, okay. Let's start then. All right, welcome to our first seminar. And it's actually, yeah, it's kind of like, felt like a real visitor.
Yeah.
We have a real, PhD lounge with coffee, and I don't know if anybody was giving you coffee, but it's, yeah. It's great. And yes, our first visitor of the semester is Sean Liu. And he finished his his PhD at MIT with Rob Freund. Sorry, that was 2019 or 20?
19.
19, okay,
Mm-hmm.
great, yes. And apparently we have a lot of some peripheral kind of intersections besides just working in a field of optimization, because now Sean is working with a postdoc who is a student from Lehigh, who was one of the students in the group. It was not my student, but still in the group that was kind of, I was interacting with closely. And also he was an intern at IBM with Andy Kahn, who used to be, my kind of collaborator and mentor at IBM. So there's a lot of connections there, and it's great to, have fun. So we'll be talking about first order methods, which is we all love and respect. So excited to have fun here. Okay.
Yeah, so thanks for the introduction and also the invitation. It's a great pleasure for me to present my work here, in particularly here, because there are so many wonderful optimizers in the group. Okay, so I'm going to talk about a first order method for linear programming, both the theory and the computation. So actually I initiated this project maybe in 2018 when I was still a student at MIT. And I was doing an intern at Google. One day I talked with Miles Rubin. Some of you may know him. He's the author of Jump. And we discussed about linear programming and deep learning. And it turns out that if you think about it, the size of the neural network you are able to solve nowadays is way larger than the LP you can solve. On the other hand, LP, maybe the simplest optimization problem, and deep learning should be much harder than LP. So what's going on? Something must be wrong. So that is the initial point of our discussion and also this project. Yeah, it's a pretty fun journey, and I'm going to show you some of our computational results as well as the theory results. So here is my collaborators on this project. So I would say this project wouldn't reach to the current stage without the wonderful engineers. In particular, David Applegate, Miles Rubin, and Warren Strudy. They were at Google, and they did wonderful engineering work. Adam is a postdoc working with me at U Chicago. Matthieu was here. He did a summer internship at Google working in our team. So Oliver is at U Pittsburgh right now. Brandon is at DeepMind. So Jimmy is a student working with me at U Chicago. So the talk today is essentially based on 3 of our papers. The first one is more computational, second one is more theoretical, and the last one is still in preparation. And indeed, I'm going to present some of the very recent results I got maybe 2 weeks ago, which is pretty fun. That is for the last paper. I also want to mention that we now have an open source solver based on the method we proposed. It's called Pdlp. It's open source through Google OR tools. Here is the link. Just want to quickly show you. It's very easy to use. Essentially, there are Python, C++, Java, C interface. Just need to define the variable, define the constraint, define the objective. Then you use the solve. Then you can use our solver to solve this problem. We also have We can also like use cvxpi to call Pdlp. I mean, again, it's very easy to use. If you ever want to try it, the solver, please just do that. And if you have find anything fun, let me know. Okay, so in the title of my talk, I have two terms, linear programming and first order method. In this audience, I don't think I need to introduce what they are, but just like a very high level recap. So linear programming refers to a minimization problem, like where the objective is linear, constraint is a polytope. So first order method refers to optimization method based on gradient information. For example, like a gradient descent and all of its cousins. So many of you may have this question, like is LP a solved problem? There are similar claims even in 1970s. Like when taking the LP class at MIT, I had the impression that like LP is solved because like, I mean, we can use like the Groovy or simplex to solve almost all of the LP, at least like in the textbook and also maybe in some of the research projects. I mean, the modern commercial LP solvers, they are very reliable, like Groovy, they are good at like solving, providing like a very high accuracy solution. So on the other hand, like after working at Google, I realized this is not the case. The fundamental reason for that is because the data at Google, they always store in a distributed system. And LP, all of the LP solvers, they are only work for a single machine. Okay, so in other words, like these LP solvers, they are not suitable for the big data type, where the data they are stored in a distributed system. It's not like a feasible tool. Okay, that is like exactly where I want to work on. I want to try to extend the current LP solver, I mean, just to develop a new algorithm that can work for the distributed system. I mean, there is indeed some reason for this. If you look at the history of computational LP, there were like two previous golden periods. First one is like from like 1947 to early 1970s when simplex method was developed. The second one is from like late 1980s to early 2000s. That is like when barrier method was developed, dual simplex method and sparse linear algebra was used like in LP solvers. These are all happens before we enter the big data time. Like back then, even though there is a distributed system, like people do not care too much. And now everybody care about distributed system, like because the data they are always stored in the distributed system. So indeed, like we all know, like the state-of-art LP solver are either based on simplex method or barrier method. Indeed, there is like a scalability issue for these two approach. It's very hard to further scale them up. The fundamental reason for that is because for both methods, the bottleneck is solving the linear equation. It's a highly challenge to solve a linear equation in the distributed setting. There are two issues. Like one is like this parallel computing or distributed setting. Simplex method, no matter how many threads you use, there is at most like a 2 times speed up. So barrier method is better, but it's limited to like a multi-threaded CPU, like a single machine, shared memory, multi-threaded CPU. And maybe like after 20 threads, you can no longer see any improvement. And the total improvement with like multi-threading maybe like 4, 5, 6 times faster. For barrier, that's the most if you try out like Groovy. And this is like not so good like in the distributed system. And furthermore, there's another issue, this memory issue. When solving a linear equation, you need to store the factorization, not only the constraint matrix, but also the factorization. In the world of LP, the constraint matrix itself may be extremely sparse, but the factorization usually is like much denser, like 10 to 100 times denser than the constraint matrix. So that is why, like even in a single machine, even though you are able to store the problem, when you try it on Groovy, it may give you like a memory error because the factorization is larger. Okay, so these are the bottlenecks, like why it's very hard to further scale up the existing method. That is also why like, we want to use a new method, like first order method, because first of all, order method, the bottleneck is the computational bottleneck is like a matrix vector multiplication, and there's no factorization, so memory is not an issue. So furthermore, like sparse matrix vector multiplication is very well studied, and it can scale well on like a modern computing architecture, like a multi-threaded CPU, GPU distributed setting. So thanks to the development of deep learning. Okay. So another question you may have is like how large an LP you can solve nowadays. This is not a well-defined question because for some of the LP, maybe you can use the special structure of the LP to develop like a special algorithm. For example, if you think about like a minimal spanning tree, so one can use a specialized algorithm to solve the problem with 10 to the 9th nodes. You can formulate the problem as an LP, then it's become like a 2 to the 10 to the 18th constraint. You cannot even store this problem using all machines on Earth, but still you can have a specialized algorithm to solve it. Another example is like a two-stage statistic programming. There is a special purpose like decomposition algorithm. By utilizing distributed computing, you can solve a problem with like 500 million variable and constraint. Okay, what if you do not use any special structure? You like treat it as a general purpose LP. There is a 2019 stack exchange question. The largest instance mentioned in that question is this instance with 325 million on zero. And it took like a barrier method like 5 days to solve the problem. So this is roughly the scale like the problem one can solve by using like a general purpose solver. I mean, it's consistent with our own try. We have a series of like TSP cutting plan lower bound instance provided by Bill Cook. And the largest instance we are able to solve using a 1 terabyte memory machine using Groovy. It has like a 475 million on zero. I mean, roughly this may be the scale one can solve using commercial LP solver. And also like this is not always the case. We also have like a very much smaller LP that Groovy cannot solve. For example, we have this like a PageRank problem with only like 800,000 non-zeros. Groovy failed to solve because the factorization is way denser than the original constraint matrix, and it just cannot store the factorization. So on the other hand, like the largest instance we are able to solve has like 91 billion on zero. This is roughly maybe 200 times larger than Groovy can solve right now. And we use like 2000 CPU to solve this problem. I mean, to store this problem, I mean, you need a distributed system to store it. It cannot be stored on a single machine. But like, I mean, this is our goal, roughly speaking, like maybe 1,000 times larger than Groovy can solve. Okay, so here I also want to mention that like first order method for LP is not a new idea. So there are early works on this, like even since the 1950s, but none of the early work was numerically successful based on a review paper by Bixby. Recently, this idea, like first order method for like LP, re-emerged due to the large-scale applications happens in like just in the data sense. And here are a few different approaches. Like SCS is a ADMM-based algorithm. I mean, it's more for cognitive programming, not only for LP, but you can use SCS to solve LP. It's developed by a group of like Steve Boyd. Like AB is a like ADMM-based interior pointer method developed by Yin Yi and his group. And also Kim Chuang-To and Defeng Zhang and his group developed like a semi-smooth Newton method. Rahul Mazanger and his friends at LinkedIn has like a method based on natural smoothing and accelerated method. I mean, compared to maybe the first two, like we are in general like, much faster in the context of ILP. And compared to the last two, they are very good at like solving like maybe very fat or very tall LP, not for general purpose LP. Just want to quickly mention this. Like this is not like, I mean, it's like there are different groups of people are working on this idea. Okay, so in the rest of this talk, I'm gonna first talk about like the algorithm, our proposed algorithm, and present to you like our computational results. Then I'm gonna dive into theory and talk about like how we are able to achieve like faster convergence by using a simple idea restart, and also by introducing like sharpness for our primordial problem. And finally, if I got enough time, I'm going to talk about the geometry and the behavior of the algorithm, and also the refine rate. Okay. So here is the standard form LP, a mean Cx such that Ax equal to b, x non-negative. So we look at the primordial form of the LP, where we dualize this Ax equal to b constraint. by introducing this y variable, the dual variable y. Now the problem becomes a min-max problem. Min over x, max over y, and we are trying to find a stationary point or saddle point for this problem. So the basic algorithm we use is called the primal dual hybrid gradient, proposed by like Chambo and Pog about 10 years ago. So here is the algorithm. It's a very simple algorithm. So x plus and y plus are the next iteration, the primal dual variable for the next iteration. X and y are the current solution. So this eta and the tau are the primal step size and the dual step size respectively. And here this is a projection to the positive quotient. So as you can see, the major cost per iteration is the matrix vector multiplication, a transpose y or ax. Okay, this is indeed like the most computationally expensive part for this algorithm. And in the early work of Chambo and Pog, ask any question to interrupt me whenever you want. Yeah, I mean, it can be fun to take questions. And here I also want to mention like why Pdhg, right? The reason is very simple because we tried out like many different algorithms. Pdhg works the best numerically. So here is a subset of the algorithms we tried, and a few algorithms we study here, like James' algorithm or Ben Grimmer's algorithm, and also like a non-smooth BFGS by Adrian and Michael Overton. Yeah, so like turns out like just like a Pdhg somehow works the best numerically. Here, what I want to mention is like Pdhg itself doesn't work that well. We have a benchmark set with like 383 instances from MIPLib. We look at the LP relaxation, the root node LP relaxation. So the vanilla version of Pdhg can only solve like 40% of the instance to this like 10 to the minus 4 relative accuracy. Not very good, and like 19% of the instance, which is high accuracy, 10 to the minus 8. So this is perhaps like the reason why in the early work on first order method for LP doesn't work that well, because the vanilla version for the algorithm doesn't work well. And like our proposed algorithm, we call it like a Pdlp, like a primal dual algorithm for LP. So we utilize like many enhancements on top of Pdhg, trying to like trying to utilize the structure of the LP. So here is the subset of the major techniques we developed in Pdlp on top of Pdhg. The first one is the adaptive step size. Okay, so it's a first order method. So how to choose the step size is critical. The step size guaranteed by theory is too conservative. So we need to like use like a more aggressive step size rule by using this adaptive idea. Second one is like diagonal preconditioning. So for first order method, the convergence guarantee is driven by the complexity, the condition number. And we are doing like a diagonal preconditioner trying to improve the condition number of the problem. So the next one is restarts. I'm going to talk in more detail about these restarts in the next session. So essentially, by using restart, we are able to show that the algorithm can achieve the optimal linear convergence rate. And another thing is like infeasibility detection. So in the world of LP, very often the problem is like infeasible or unbounded. It turns out that like the Pdhg iterates encode information of the infeasibility. So if the problem is infeasible or unbounded, the iterate is going to diverge like a ray. And the direction of the diverging turns out to be the infeasibility certificate for the problem. Another thing is this primal weight update that is trying to balance the primal infeasibility and the dual infeasibility. Last one is like a pre-solving. It's just trying to utilize maybe some open source LP solver, trying to reduce some of the like, redundant variable or redundant constraint. This is like the basic idea of like our enhancement on top of Pdhg. These are really crucial because without it, you cannot solve much problem. So with all of these enhancements, the Pdlp can solve like 97% of the instance to this low accuracy, 10 to the minus 4 relative accuracy, and 85% of the instance to 10 to the minus 8 relative accuracy within 1 hour. So this is like it's maybe good enough to support an LP solver. The previous one is not. Okay. So next, I'm gonna do some present some like comparison, like with different solvers. I'm gonna talk about a comparison with Groovy, we're gonna look at like a few different benchmark sets. First one is like this medium-sized make-believe benchmark set. So overall, Group B works better than us, but we are faster on a specific instance. I'm gonna also talk about like the Mittelman benchmark set, and then I'm gonna talk about like a few larger instances which are more interesting. And this larger instance is like larger than 10 million non-zero and less than 100 million non-zero. So I would say the story here is more like instance dependent. Like for some instance we are faster, some Group B may be faster. And for even larger instance, like for example, instance larger than a billion non-zero, then Group B is no longer a feasible solution. So our method can still work. I'm gonna also compare with GLOB. So GLOB is an open source implementation of the simplex method. It's a fairly good implementation, not as good as like Group B. I mean, the reason to compare with GLOB is more like because our solver is also in the first stage, it's open sourced. There are many enhancements we can improve. Group B is already developed so many years, so comparing with like Group B may not be always fair. That's why we also want to compare with like some open source solver. And finally, I'm gonna mention like with like multi-threading and distributed system, what are the improvements we can see? Okay, essentially for a large enough instance, we can see how much the distributed system is helpful. Okay, so here is the results. The comparison with Group B. So Group B outperformed Pdlp overall. It's not surprising. Group B is over-optimized in this benchmark set. What is interesting to us is like there are quite a few instances like we are faster than Group B. So here I also want to mention that like this is using the Julia implementation. It's like a first prototype. Our C++ implementation may be 5-6 faster than this. But still, like what is interesting is like, for example, in this EX9 instance, like Pdlp has like 1.6 second you can solve to like very high accuracy. It's fast, maybe like 20-30 times faster than Group B. And like, so what is fun here is like, even though Group B is like over-optimized on this benchmark set, so there are still instances we are faster. So we are not suggesting like we're gonna replace Group B, of course. It's more like maybe we can use all the algorithm simultaneously and use the fastest algorithm. It can be like running a portfolio, like what Group B is doing for barrier and simplex. And then is maybe you can improve on quite a few instances. So here is a comparison on the same benchmark set with GLOB. So Pdlp is faster than like GLOB primal simplex on 46% instance, and 10 times faster on like 23% instance. And compared to dual simplex, so Pdlp is faster on 41% of instance, and 10 times faster on 18% of instance. Again, the story is like maybe you can use it as a portfolio. I mean, it won't beat Group B or simplex. It won't replace simplex, in particular for the like medium-sized instance. Okay, so like, but like still, maybe when you run multiple algorithms at the same time, you can maybe get a faster solution. Okay, so here is a screenshot from like Mittelman's web page. So Pdlp is listed in the barrier benchmarks for barrier, and like so the first barrier solver now is like COP, and the Pdlp is here is listed fifth. You see like the running time is maybe like 13 or 14 times longer than COP, but still like Pdlp may be faster compared to other open source solvers. Okay, so now let's move to like a few like larger instance. So here is a large scale application I'm working with with a department store. So the goal here is essentially trying to give different promotion to different households. And we have like 4 models for this problem. It's reasonably large. We use the data from like 3 states. And the problem has like maybe it's like over 10 million zeros in the problem. And at least for this problem, Pdlp works very well. You just need like a few hundred seconds to solve to 10 to the minus 6 relative accuracy. But Group B needs like over 10,000 seconds. This dash means like Group B failed to run because of the memory issue. Okay, so for this instance, like we are much faster, maybe 100 times faster than Group B. So here is another instance. It's on the PageRank problem. So this one is for real data set, and this one is more for like synthetic data set. So we can create like a data set with arbitrary size. And like what is interesting here is like when we enlarge the size of the instance, like maybe 10 times larger, then the running time for PDG may be like 20, 30 times longer. And that is like it's fairly linear. This is consistent with what we saw in other problem. If it's the same class of problem, if you enlarge the size of the problem, I mean the running time of Pdlp is like sort of like proportional to the size of a problem. But for groupie, barrier like it's different, and also like simplex, they are definitely nonlinear. Okay, when the size of the problem, I mean barrier is it's definitely nonlinear because you need to solve a larger linear system. So simplex method, for some instances, it can be linear, depending on the sparsity pattern of the problem. But overall, it's for this, at least for this instance, like it's highly nonlinear. It may be like n squared or n cubed. And the fundamental reason for this problem, the issue like groupie doesn't work well for this problem, is just because like factorization turns out to be much denser than the original matrix. So for the previous two examples, like we are faster than groupie. So here is another instance. It's like it's a robust optimization problem for like a production inventory problem. For this problem, it has like about 20 million on zero. It turns out that like groupie primal simplex works very well. Primal dual simplex and primal barrier doesn't fail to give you any solution with a reasonable time. But like primal simplex works very well. It can solve the problem to optimality within like 11,000 seconds. The PDHG doesn't work that well. It's like you can only get like a low accuracy solution within 26,000 seconds. Okay, so this is like on the other extreme, maybe groupie can still be better than Pdlp, even on a fairly large instance. Okay, and like my intuition for this problem is that like this problem is like a highly degenerate, and like somehow the optimal solution for the primal problem is a huge subspace, and primal simplex just need to find one of it, and that's why it's fast. But like ours, somehow the condition number doesn't work, that isn't that good, so we need to get longer time. Question?
Yeah, I mean, so this is sort of generic through a lot of the results you've talked about today, but here it's sort of most exposed. I mean, you're comparing apples and oranges, right? You're comparing Gurobi's optimality and Pdlp to, you know, tolerable but reasonable accuracy. I mean, how does that affect the overall sets of comparisons?
Yeah.
If you are looking, you sort of keep the threshold of what you're looking for constant.
Yeah. So actually, for the small size instance of this, the comparison is like we look at the 10 to the minus 8 relative accuracy. This is all exactly. It's kind of like you already solved the problem exactly. So I mean, if you think about like, so simplex is gonna solve it really exactly, but barrier method, roughly speaking, you solve the problem with like 10 to the -8 or -9.
In some extent, it depends on the sensitivity of the problem. I mean, simplex is handicapped by the fact that it isn't solving it at another vertex. But on the other hand, if it's a relatively flat space in terms of what the objective function is, it may come within that relative accuracy. I mean, it depends on the problem structure. But it may come to within that relative accuracy much earlier, and there are ways of actually doing early detection. So if you're, yeah.
So for simplex method, at least like groupie doesn't provide like early stopping, right? I mean, you cannot set a tolerance and let it early stop. I mean, either they solve the problem to optimality, or they doesn't give you any solution. A barrier method is more like, okay, you can set the tolerance, but like solving to optimality and solving to 10 to the minus 4 relative accuracy, and give you like nearly the same running time, because like we just need like 2 more iterations to get like a solution from 10 to the minus 4 to 10 to the minus 8. So for us, we need like we need like a longer time from 10 to the minus 4 to 10 to the minus 8. So that's why.
So I guess one thing that's okay, not fair the other way, is you can report back how much earlier Gurobi actually got that level of accuracy, even if it didn't know it.
For simplex, you cannot do that, right? I mean, like it doesn't tell. I mean, there is no way to reported. But for barrier, you can do that. For
I
barrier,
mean, it depends what, I mean, again, if you're just trying to sort of analyze it after the fact, you can. I mean, you just have to do,
Oh,
early.
yeah, you can do that. Yeah, for yeah, if group is if you look at like an open source software, yes, you can. Yeah, and then yeah, so yeah, and yeah, the thing is more like 10 to the minus 4 relative. Okay, so most of the comparison what I did here is like 10 to the minus 8, but for larger instance, what I'm doing is like a lower order accuracy, because like for many applications, like indeed for the large scale applications, the low accuracy is enough.
But
Yeah.
actually, so related to this, low accuracy is enough, but you don't get a basic feasible solution.
Yeah, you don't get a basic feasible solution.
And that is probably impossible for this. I mean,
Yeah.
it's very expensive.
Exactly. So crossover
Right.
probably gonna be much more expensive than solving the original LP. Yeah, crossover can be for the large problem.
Right.
Crossover can take a much longer time.
So depending on what you're trying to do with the solution.
Yeah,
it
depend. Yeah,
can
it's
be a
really
handicap. Okay.
yeah. If you want to solve a MIP, then yeah, it's problematic. Yeah.
Right, or
yeah.
sensitivity analysis in certain cases.
Yeah. If you are just like trying to get a solution for online advertising problem, then it's okay.
Okay.
Yeah. Okay. Any other question? Yeah, but I mean, it's a good point. Like, I mean, so the tolerance we are aiming at, like, it's so one benefit of our algorithm is that like we can set the tolerance easily, and like if you set if you think like the low tolerance is enough for you, then you can stop much earlier. But for simplex, you just cannot do that. Like for barrier, it doesn't save you something. That's why like this is like another advantage for us. Like we can do early stopping and also like won't start. Okay, good. Now let's move to like a huge space, huge problem. And the largest instance we are able to solve have this like 3.5 billion variable, 400 like million string, and 92 billion non-zeros. I mean, we used like 2,000 CPU to solve the problem. It took like about 5 days to solve to 10 to the minus 4 relative accuracy. I mean, you see like this is the scale. Like when you really want to solve a large scale problem, it takes like maybe 10 seconds to solve for one iteration. I mean, it can take a long time, and your goal is not to solve to optimality, but perhaps like 10 to the minus 4 accuracy. This is roughly the scale you may want to solve. And next thing I want to talk about is like.
Question. So is this not a contrast problem, right? So how do you know that 10 to the minus 4 accuracy?
Oh yeah. So we look at the primal feasibility, dual feasibility, primal dual gap, similar to what group we had. And we look at these three value and get like the relative tolerance. Yeah.
And just to nail down the specifics, this is a subtotal elimination LP for what size instance?
So
I mean, when you say a big TSP LP instance, I want to understand what that means. I assume it's a subtotal elimination LP.
Yeah.
And that's on how many nodes and how sparse of edge set?
Yeah. So yeah, I don't know. I mean, I used to know that, but now I forgot. Like it's an instance provided by Pdlp. So Pdlp has I mean, a series of TSP instances that they want to solve, and it can be very large. And we use it as a test set to the distributed system because it can be very large. It's kind of like you are trying to do the TSP on the galaxy. Yeah, as like 3D galaxy, like you want to do that, like use all the stars people already discovered. Yeah. Yeah.
So to follow up on Jim's question, so when you say 10 to the 4 accuracy, it is a combination of optimality gap and
also the feasibility. Yeah.
Primal feasibility.
Yeah, primal feasibility.
And
dual
yeah,
feasibility.
we don't have a primal feasible solution.
Yeah, I don't have a feasible.
Some infeasibility, some optimality.
Yeah, it's like it's no minus 4. It's like it's not exactly feasible, but it's like no minus 4 relatively fit. I mean, it can be it's not really feasible. Yeah. Okay, great. Any other questions? Okay. So here I want to show you like how multi-threading and like distributors can help. So here, so so the baseline is like the 4 threads shared memory machine, and the blue bar here they are like multi-thread shared memory machine. So red bar here are the distributed system. And like with 4 thread is 1. And then you see like this is a speed up. The value is a speed up. With 8, maybe it's going to become 2. And with 100, it's going to become like 16 or 15, something like that. It's like with 100 threads, it can be like 15 times faster than 4 threads. It's fairly linear if you look at this. And furthermore, for the distributed system, so there's going to be an overhead. Okay, with like 50 cores, maybe it can be like 3-4 times faster than 4 core. But like with like 1,000, it's going to be like 60 times faster than 4 threads. So you see, still like it's fairly linear. I mean, so by that, what I want to tell is like, as long as the size of the problem is very large, then you can do the partition of the data carefully on the different machine, and the computational bottleneck is gonna be kind of like speeded up. It's like roughly like a linear growth. Yeah. Okay, so that is like the computational results. So any other questions? And then I'm gonna move to the theory side. Okay, the first thing I'm gonna talk about is like how we are able to achieve like faster linear convergence by using restarts and sharpness. Okay, so the traditional results of PDHG, if you apply it for LP, is mostly not sublinear because LP is not strongly convex. And if you look at the last iteration, it's going to have like order 1 over epsilon convergence rate, complexity. If you look at the average iteration, you're going to get like order 1 over epsilon. I mean, this is a sublinear rate. It's not enough to support like an LP solver because for most of the LP, people maybe expect like a high accuracy solution, at least like 10 to the minus 4. Okay, so if the 10 to the minus 4, the average solution, if it's order 1 over epsilon, it's going to be tricky already. But that's why we want something like that has a linear convergence, at least. Okay, so the question we want to answer here are like, first, like, is there a version of PDHG that can achieve like a global linear convergence when solving LP? So furthermore, is the proposed algorithm optimal? Are there possibly better algorithm? The answer to the first question is yes. We have like a very simple variant of PDHG that's going to give you global linear convergence. And furthermore, we can show that like a proposed algorithm is optimal. I mean, there's no better first order method that can achieve like a better complexity. Okay, so here is our algorithm. So it's a variant of PDHG. It's a 2-loop algorithm. Okay, the idea is straightforward. Okay, so you have in the inner loop, you're going to run PDHG. And then you're going to look at the average iteration inside this like inner loop. And you're going to return the average solution in the inner loop. And then the outer loop going to take the average in the past outer loop at the starting point, and then rerun the algorithm. I'm going to show you a simple example in the next slide that can help you better understand the algorithm. Here, what I want to highlight here is like when to restart. That is very important here. And we propose like 2 restart conditions. One is like if a certain problem parameter is known to us, we can do fixed frequency restart. Otherwise, we also have like an adaptive restart scheme. Okay, so here is a simple example. We look at like a min-max problem, min over x, max over y, x times y. So 0, 0 is the unique stationary point. So this blue line here is actually the iterates of PDHG. It's essentially a linear dynamical system, and you can get like a closed form solution. It's gonna spiral in like ellipsoid. So here is the average iteration. The red line is the average iteration. That means like maybe the 5th dot here in the red line gonna be the average of the first 5 dots in the blue line. Okay, this is the average iteration. The average iteration may be slightly faster than the last iteration. Okay, so this is our restarted scheme. Basic idea is like at the beginning, it's gonna overlap with the average iteration. And then at this point, we're gonna restart our algorithm. By restarting, it means like we're gonna forget all of the previous history. And we're gonna, starting from 0, calculating the last iteration, and calculating the average iteration, and forget all of the average like before that. Because like I mean, if you think about like every iteration, I mean, the every iteration like a long time ago, the information a long time ago shouldn't matter too much. And that's why like you perhaps should do restart. And at least like for this example, you can see the green line converges much faster than to the origin, that is the stationary point, than all other lines. Okay? So.
So when you take the average, you really take the average. There's no weights that put more emphasis to the more recent iterates and
yeah.
There's a purpose for that.
That's a great question. Yeah. So so actually what we are using is like when you use constant step size, then you should do direct average. If you use like adaptive step size, then the weight should be your step size. Yeah.
So that's a theory result, or that's what works in practice?
There is some theory behind it. Yeah, it's like just like when you take the average, I mean the step size is gonna be essentially it's a complex optimization problem. So like when you do the combination, somehow it's kind of like you should take use the step size as a weight, so that like when you do the using the like complexities, then you can get what you want. Yeah. And that also happens in like, for example, subgradient descent. To solve a minimization problem, then you should use the step size as your weight for the average. Okay, good. Okay, so next I'm gonna introduce in order to analyze this algorithm, we need to introduce like a few new concepts. The first concept is like normalized duality gap. So here we consider a generic primordial problem first, like mean over x, max over y, LXY. The traditional progress measurement for a min-max problem is primordial gap. Is this one here? Okay, so as a solution xy, so we use like z to represent x and y together, just for simplicity. As the current solution, we calculate the primal value, we calculate the dual value, we look at the primordial gap. And we can rewrite it as this one here. So however, the primordial gap is not a good progress metric for LP. The reason for that is because in LP, this L is bilinear. Constraint is unbounded. And then this primordial gap is going to be infinity for most of the solution. It's not informative. That's why we need to come up with like another progress measurement. Okay, so our progress measurement is this like normalized duality gap. So the basic idea is that like duality gap, you take the mean or max, you're going to take it like in all the space, all the feasible region. So what we are taking is like we take this z is x and y together. We take this z inside a ball around the current solution. Okay, so that's the basic idea. We don't take the maximum over the whole space. We take it like around the current solution. And then this gap here can always be finite because it's inside a ball. And the value of this gap gonna be sort of like when r gets to infinity, this gap gonna be infinity. That's why we're gonna normalize it. We're gonna use like 1 over r times this gap. Okay, this is like a concept we propose called like normalized duality gap. And at our optimal solution, this normalized duality gap can always be 0. And for any finite solution, this rho z can always be finite. Okay. Furthermore, it turns out that like at least like for LP, there is an easy way to calculate like rho z. There is a linear time algorithm to calculate the normalized duality gap, easy to evaluate. So another concept I'm going to introduce is the sharpness for the primordial problem. I mean, sharpness is a standard like condition for a minimization problem. Here is the definition. Essentially, it means like the optimality gap is going to be larger than a constant alpha, that is larger than 0, times the distance from the current solution to optimal solution. Okay, this means, for example, like the absolute value is a sharp function, but x squared is not a sharp function. So the sharpness condition is well used for minimization problem, but for primordial problem, it's not that well defined. So here we introduce like the sharpness for the primordial problem. Essentially, we call the primordial problem is sharp if the normalized duality gap is sharp in the standard sense. Because like we know like at the optimal solution, rho R optimal solution going to be 0. So this is essentially it's trying to see like this rho RZ is sharp in the standard sense. Okay, and it turns out that like LP is sharp. So LP is alpha sharp, and the value of alpha is this value here. Here, HK is a Hoffman constant of the KD system. And besides that, like, there is also something like this distance from the initial solution to the optimal solution. So what happened here is like LP is not globally sharp, but on any bounded region is sharp. And we know that like when running PDHG, we know it's a like a non-expensive operator, so we know it's going to converge into an optimal solution. So that's why like you can never go to infinity, and that's why like the sharpness constant going to also include the initial distance to optimality set. And like we know like LP is alpha sharp, and by utilizing this feature, we are able to propose like two different restarting schemes. The first one is like the phase frequency restart. That's going to assume this alpha is known to the user. We also have another parameter, this gamma. Gamma is the smoothness constant of the problem. In the case of LP, it's essentially that L2 norm of A. Suppose both values are known to you, then the theory suggests to use this frequency to restart your algorithm. So in practice, calculating gamma maybe is easy, but calculating alpha is much harder than solving the original LP. And that's just why like we can also introduce like an adaptive restart scheme. The basic idea of the adaptive restart scheme is like whenever the normalized duality gap become a half, then you restart your algorithm. Because the normalized duality gap is easy to calculate, so I mean it's a tractable algorithm. Okay, so any question about this part, like the different restart scheme?
Can you explain more the intuition behind the adaptive restart?
Yeah. Okay, so the adaptive restart is like, okay, roughly speaking, we want the normalized duality gap to go to 0. This is our goal. And then it turns out that like, without restart, one can show that like this rho RZ after k iteration gonna be smaller than maybe constant divided by k. It's gonna have some linear rate if you do not do restart. And then if you do restart, okay, if you do restart, like essentially whenever this rho RZ becomes a half, you restart. And how many iterations do you need to restart? It's gonna be like maybe 2k. After 2k iteration, 2c iteration, you're gonna restart. Okay? So every 2c iteration, this rho RZ is gonna become a half. That's why you can get a linear convergence. But the issue is like, if you know C, you know when to restart. If you do not know C, you just look at it whenever the rho RZ become a half. You start your algorithm.
Okay. So does it have anything to do with the sharpness of your...
Yeah, exactly. So like, I mean, this value here, I mean, this C gonna depends on the sharpness. Yeah, and like how many iteration this rho RZ gonna become a half gonna depends on the sharpness constant.
Okay.
Yeah.
Thank you.
Yeah, great. Okay, so here is our theoretical guarantee. We show that like suppose the primordial problem is like gamma smooth alpha sharp, then the restarted PDHG gonna have linear convergence, and with the linear rate like gamma over alpha. Okay, so this theorem works for both like a phase frequency restart scheme and also the adaptive restart scheme. So furthermore, we are able to show that indeed, like this bound here is the optimal bound. In other words, like no first order method can achieve better than this complexity when solving a sharp and smooth primordial problem. We have a worst case instance, and it shows like no better algorithm can be achieved better than this bound. So together with these two results, it shows that like a restarted PDHG achieves the optimal linear convergence rate. Okay, so any question about this part? Right?
if it's easy, what is the counterexample like? It's an LP.
Yeah.
Are we talking about the LP or?
Yeah, it's LP. It's even simpler. The counterexample is more like it's an unconstrained bilinear problem. It's like something like this. Like mean over x, max over y, x transpose AY. And this A matrix is gonna look like something like this. 1 minus 2, 1 minus 2, 1, blah 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 blah. And then if you are familiar with like Nesterow's worst case instance, then this is essentially like a Nesterow's worst case instance for a minimization problem on a primordial problem. Yeah. But it's like it's a simpler problem. There's no constraint. Yeah. There's like no negativity constraint. Mm-hmm.
So maybe I got lost somewhere here, but why is your LP should be a polyhedron, so why would it be smooth?
Oh, smooth means like, okay, so because like Lxy, so by smooth I mean this L is smooth, it's differentiable. Lxy is essentially it's essentially this one here. Lxy is this one, so it's smooth, it's differentiable, right?
Okay.
Yeah, it's like bilinear function. Okay, great. Okay, so here I also want to mention that like in a more recent work we are able to show that like PTHG, the vanilla PTHG, without restart can also achieve linear convergence rate. So however, the linear convergence rate is going to be worse than restart, like it's going to have a square. And this is like, this bound is tight, so that means like restart does help the convergence of the algorithm. Yeah. Okay, good. So next I'm going to talk a little bit more about like the behavior of the algorithm and the refined complexity. Okay, so the previous part of it shows this regret bound. This is like complexity results. So however, there is some issue here. Fundamental issue is like this bound here turns out it doesn't match with the behavior of the algorithm too much. I'm going to show you some behavior in the next slides. A fundamental reason why there is this mismatch is because this value of alpha depends on the Hoffman constant of the KKT system. And it's known that like the Hoffman constant of the KKT system is going to be a loose bound. And there isn't like a good characterization of the Hoffman constant for this linear system. Like one of the characterization, maybe this one here, essentially you need to look at like every subset of the matrix and then calculate something. It's combinatorial, so like it takes exponential time to calculate the Hoffman constant. And this value is fairly loose. It can be very small. Hoffman constant can be very large. It can be too large to characterize the convergence. And that's why like we are thinking about how to further improve the complexity. And here is the behavior of the algorithm. So here in this figure, x-axis is the iteration, y-axis is the KKT residual. It's like primal feasibility, dual feasibility, and primordial gap. These 5 lines here are for 5 different instances from MIPLib. You see, for some instance, maybe can have like a very fast convergence, like this purple line. For some instance, like this black line, it's gonna flat out. It's a very slow convergence. And this red line, blue line, and the green line, they may be flat out for a while, and then you see the linear convergence. So this behavior is fairly general. If you look at a random instance from like MIPLib, you're gonna see it's probably gonna be one of this type. So however, the complexity bound with the linear convergence rate we saw before cannot characterize this behavior. That is what I'm trying to do here, like how to characterize this behavior. Is there any question? Mm-hmm.
Why are there oscillations?
Oh yeah.
You're using a first order method on a smooth objective, shouldn't it?
It's a primordial problem. Okay, so why is oscillation? Okay, it's very easy to explain. It's because like, so you see here it's gonna spiral in as an ellipsoid. Mm-hmm. And like if you use L2 norm to measure the distance to optimality, it's gonna oscillate. Okay. And when the condition number is pretty bad, it's gonna oscillate dramatically. Okay. Yeah, that's the reason. Yeah, because just like you are not using the right norm in some sense. If you use the right norm, it's gonna be monotone.
I see. I see.
Yeah. Okay. Okay. typical behavior of this algorithm is more like it can be characterized like something like this. It's gonna always be like maybe they're gonna be two stage. First stage gonna have like slow convergence, and second stage gonna have like a faster convergence. Difference may be like how long is the first stage. For some instance, the first stage is very short. Some instance is very long. And also another thing is like in the second stage, how fast is the rate? Maybe this green line is slow, red line is fast. So what other for what type of problem you're gonna have like a longer first stage, and what is the driving force for the second stage? That is what we want to answer here. I'm looking at the time. I'm like maybe 4 minutes. So I just want to quickly show you like a simple two-dimensional example, and that indeed can characterize the behavior of all of this what is going on here. In this two-dimensional example, it's like when you look at the dual LP, and the dual LP is like maximize B transpose Y such that A transpose Y is smaller than C. And here is the LP. The gray area here is the feasible region. North is the direction to go. And so we have like two parameters of the LP. We look at like a class of LP which has like two parameters, kappa and delta. Kappa is essentially the height of this top vertex. So we wanted the kappa to be in between 0 and 1. And this kappa essentially measures like the condition number of this matrix A. And another constant is this delta. So delta is like, you see this flat line here. The delta means like how far away this flat line is from the top vertex. Essentially, when delta is equal to 0, these three lines gonna collapse. And you're gonna have like an intersect. And then the problem is degenerate. And when you have like very small delta, the problem is like near degenerate. When delta is large, then you have like a very it's like very non-degenerate. So here is the behavior of the algorithm when using like different kappa value and the delta value. So essentially, the kappa value gonna kind of like capture the linear convergence. When kappa is large, the blue line and the green line, the eventual linear convergence is gonna be large. So delta gonna measure like how flat, how long the first stage is. This green line, the first stage is very long. The purple line, the first stage is very long. That is because this delta value is close to 0. So in other words, like what we found out is like when the problem is near degenerate, then it has a very long first stage. Okay, and like when the condition number gets better, you're gonna have like a faster linear convergence. So everything I talked about here can be formalized. Okay, so the basic idea is like the fundamental idea is like utilizing this concept of like a partial smoothness, like developed by Adrian here. And essentially, in the first stage, you are trying to identify the active basis. In the second stage, once the active basis is fixed, and you can throw out like a non-irrelevant constraints, and then the linear convergence is going to be much faster. Here, I also want to mention that like you cannot use like the partial smoothness concept directly, because if you use partial smoothness, there is an assumption like of non-degenerate. But in real LP instance, the problem are always degenerate. So we are able to dealing with like degeneracy, like how degeneracy gonna affect the convergence by loop in the case of like LP. Okay, so I'll probably in 1 moment later. Yeah. So, and I mean here, I don't want to go to much details here, but here is our complexity, eventual complexity. So delta is how close you are to degenerate. I mean, essentially, degeneracy itself doesn't matter, but near degeneracy makes the problem harder to solve. And then we have this complexity have like two parts. One is like this, like how close you are to degenerate. The other part is like from delta to epsilon. That one you're gonna have like a better linear convergence rate. So the first part is gonna depends on delta. Okay, that kind of like, it sort of like explains what is going on here. So this problem maybe is like close to degenerate, so that's why you see like a flat out for a while, and like the linear convergence kind of depends on the condition number in the end. Okay, that is like all I want to talk about here. I'm gonna end my talk here. Just want to quickly mention that like there are like many potential extensions of this work. Like for example, can we do QP? Can we do SDP? Can we extend the work to mixed integer programming, etc., etc.? I feel like it's a very exciting time because there are so many wonderful applications, large-scale applications in practice, and like there are like new algorithms and new theory. It's very fun. Okay, I'll end here.
So going back to what Octave said, which is this doesn't necessarily give you something that's feasible. You just confound the feasibility gap.
Yeah.
So suppose I do. So do you have a heuristic to map you back to a feasible solution, and do you have some idea about how much optimality you lose?
Mm-hmm. Yeah. So like the first question is like, yes, we have something. I mean, it's still under development, but like we have something that can sort of like. I mean, it's not like this, but it's sort of like dragging you back to the feasible region. You lose a little bit more of optimality, but it's making you more feasible. We have some heuristic to do that. Like we are still developing that right now.
Okay.
Yeah, but like, yeah. So right now the metric is still like it can be slightly infeasible. Yeah.
Okay.
Yeah. Okay.
It's maybe not very relevant to the talk. What's the OR, Google OR tool? Can you use maybe a few seconds to just plot, advertise it or something?
Yeah. Google OR tool is like it's a toolbox like similar to TensorFlow provided by Google. It's open source. Like you can use it to solve like different type of optimization problems. They are good at like set, for example.
So it's not necessarily using Google machine.
Not using Google. It's open source. You can call it in other machines, like similar to TensorFlow, like you install the package.
Cool.
Yeah.
So when you talk about very large problems, big data, I know, there is usually a structure in the constraint matrix. Things repeat, logs, something like that. Can this method exploit such structure?
Yeah, that's a great question. Like, so first, like the current version of our algorithm doesn't utilize that, and actually, it's possible to use that. So essentially, I mean, for example, here, let me just try to go back to the algorithm. Okay. So in the algorithm here, so here we directly do the projection to the positive offset. Indeed, like for example, we can also put some constraint into the projection. For example, if we know some of the x are in the standard simplex, and we know how to do the projection to the standard simplex by using like maybe Bregman divergence, then we can put the in particular for many matching problem, allocation problem, x is on the standard simplex, and then we are able to just put it in the projection part that can better utilize the structure. But on the other hand, we do not utilize the general structure or the block some general structure. It's more like if you have an LP with structure that you really want to solve it, maybe you can explore the structure. But think about it's a general purpose solver, so many people may not have the engineering power to build up a specialized solver, right? So having a general thing can be helpful.
Shouldn't matrix multiplication can in principle use a structure, right? You're using matrix vector multiplication all the time.
Yeah, we use. There is more no need to use the structure. So you can use the structure to better partition your data. There may be a network structure, and you can partition your data on different machines better. Yeah, that is something like we are kind of like we are trying to do that. Like yeah, that is something we are doing. But like we are not using like for example Danziger-Wolf decomposition type of thing. Yeah, I'm not using something like that. Yeah.
Or is there anyone else?
Well, there's several more questions.
Thanks. I'm kind of curious that why are there two periods? If that's because restart, shouldn't there be multiple periods?
You mean the stage, right?
Yeah.
Yeah. It turns out that like it's still like two stage. Like okay. So here is the result for restarting the algorithm. Let's show you. Okay. So what happened is more like. Sorry, it's somehow becomes slow. Okay. So even for restarts, so what happens here? What happens here is more like in the first stage, you are trying to identify the active, identify x that is strictly larger than 0, or like x that are equal to 0 afterwards. In that sense, like whether you are doing restart, you are still doing the same thing. You are trying to identify these coordinates, and that's why like for restarted scheme, you also is gonna still have these two phases. I mean, it doesn't matter too much. Like what the algorithm tries to do are sort of like the same thing. First phase is still trying to identify the basis. Second stage is still trying to like get a faster linear convergence. Yeah. Okay. Any other question?
So I guess you mentioned the identification, which I'm guessing comes from your projection step.
Yeah.
So is it obvious why? And you keep talking about distributed systems, right? Is that it? And once we go to distributed systems, the projection operators, whether the version you just told Octave or the simple version, becomes harder. So is there an obvious way to see that the projection can be done on say 2,000 CPUs?
I mean, a projection is to the positive offset, x larger than 0. So you can just like partition your variable on different machine, do the projection there.
Right. What about the version you just told Octave where you add, say, Bregman divergence or something?
Yeah, if you are trying to do that, the Bregman divergence, like the Bregman divergence is not on all variables. It's like maybe, okay, for this part of okay, so what happens is like we are working on like, for example, online advertising problem. So there like are many decision variables, like maybe the x1, x2, these are all vectors. Like all of these x, they are all vectors. Each one of them is in a standard simplex. And then you can partition this x1 in one machine, x2 in another machine. Then you can do the projection there, etc. Yes.
Thank you.
There is Adrian online. I don't know
Oh.
if we can hear him though. But maybe.
Yeah, I don't know. Can anybody hear me?
Yes,
I don't
we
know.
can hear you.
Yeah.
Amazing.
Fantastic. Great, yeah. So, Sean, like the partial smoothness that you sketched at the end, is that, do you have in mind partial smoothness of the original LP or somehow of the primal dual system?
Yeah, it's primal dual system. So that is something like I want to discuss with you like in more detail like in our meeting.
Okay.
Yeah, essentially, what is interesting here is that like, if the problem is degenerate, what's gonna happen? So here, what for general problem, I'm not sure, but like in the case of LP, what is found is like, it's okay that like, okay, so let me just quickly show you something I like didn't talk about. Okay, so here, these are a few different sets. So this B2 set is a set where strict complementary selectness doesn't hold. That is the coordinate where you cannot identify. Okay, and that is like the degeneracy. If B2 is non-zero, then it's degenerate. Okay, so what we are able to show is like after a finite time, you can identify all other coordinates except B2. B2 you cannot identify. You don't, I mean, it can go back and forth, but you can identify n, this set n, and also B1. Okay, so once these coordinates are identified, then somehow like even though they are degenerate case, like you have many manifold, you are go back and forth along this manifold, it turns out the sharpness constant is going to be the same. So you don't need to worry too much about the degenerate case. And then you get the sharpness constant there. Yeah, it's pretty fun. It's like, yeah, degeneracy itself doesn't matter. What really matters is like if the non-degenerate part is very close to degenerate, then it's going to slow down the convergence dramatically.
Got it. Mm-hmm. Thanks.
Yeah, great. Mm-hmm.
Well, I still don't quite get your start, like, kind of logic.
Mm-hmm.
So I wonder why do you use the standardized duality gap as a measure to decide when should you forget previous iterations? I mean, if you want to like see how fast we can like improve our convergence rate, then shouldn't you use something like you compare the rate to some threshold, and if this rate is slow enough, then you just try to forget everything before.
But let's do it offline. So it's like,
Okay.
yeah, let's do it like, yeah,
Sure,
we
sure.
can do it now, yeah. Yeah, so, yeah, I mean, yeah, so I can go give you like a more detailed answer to that, yeah.
Thank you.
Yeah, great.
Great. I guess we're kind of slowly wrapping up. Okay, thank you so much. And for the first year, see, there's still stuff can be done with LPs. It's amazing.
Yeah, yeah.